close to being up to date on all the videos. I have one more from last week to drop on yesterday's class and today's class. I had one corrupted file. I still don't know. So if I can ever repair it. So I'm not sure what the deal is. I thought I did everything the same as I always do it, but technology is glitchy. So there is a missing thing in there. Maybe one of these things I can repair that file. I don't know. Everything I've used on it seems to just walk. Okay. So remember, we have a midterm coming up after spring break. We've got a new set of problems out. So some homework 6 problems are out. And you have a project that you're working on. So busy times. So hopefully you're chipping away at everything. Do a problem a night. Something like that. These are actually pretty easy. There's one hard problem on there concerning complete statistics. I'll talk about what this is. I don't really care if you can do the problem by yourself or if you have to fish it out of the solution manual. I want you to see that it's hard to do these problems. It's a very difficult challenge. And I'll talk about what it is, and then I'll tell you it doesn't really matter. So as a practicing statistician, it never comes up. But I'll tell you what it is. Basically, all the data, all the information, I should say, is a sufficient statistic. This is the minimal compression of all the information, so the least amount of storage you can have and still have all the information. This is a little bit more elusive. Sometimes people say none of the information. It's ancillary. So when somebody says something is ancillary, they're saying off topic. So that's almost correct, that this is none of the information. But it's not quite right. And that's what Fisher figured out for us, is that this isn't in some sense just the orthogonal space to this. So if you're an algebraist, you might think of it that way. Sometimes there's a little bit of overlap in the information right there. And this is a mathematical condition that tells you when these spaces are effectively orthogonal. So sometimes there's a little bit of information buried in here, but not on its own. So we'll go through that definition. So on its own, there's no information in an ancillary stat, but provided something else, there might be a little bit left in there. So Fisher was outlining all these different definitions of statistics. What are the properties? And that's one thing I'm really a big fan of with Fisher is, his mathematical ability and insights to understand the mathematical properties of stuff. Saying that, as a practicing statistician, I'm just trying to figure out what theta is. Do something with it, essentially, maybe forecast out of it. So all my actions up here. Okay, so let's just look at an example real quick. So back to the Bernoulli example. I'll say we have n instances, so I'll make it bigger than 5 just for an artifactual reason down here. But a lot of sufficient statistics exist. And so the data itself is sufficient. If I take the distribution and I divide it by the distribution, that's constant. So this is also sufficient right here. It's not the minimal compression. We know what is minimal sufficient already. You can't get any lower than 1 dimension. And so just by, can't go any farther. We don't need a mathematical definition for that. This isn't minimal, but this one is. And I can form this one from those two, just by adding them together. And so this one right here is a function of that. This one right here is a function of that. This is equivalent to that. So these are one-to-one with each other. So they have the same amount of information. So what's a good estimator for P in our example? It's not the sum of the xi's, but I can use some of the xi's to build a good estimator. And so all the information is here. It's not quite provided all on its own. It will do something. So in the book, they say the definition of a minimal sufficient statistic is it's a function of any other sufficient statistic. I can take any other sufficient statistic and I can form it. Not necessarily the other way around. So I can't take this and figure out what those were. I can use these and I can figure out what those are. I can use this, and I can figure out what that is. I can use this, and I can figure out what that is. And so these statistics down here are functions of other sufficient statistics. So that's the definition they provide. Function of any other sufficient statistic. Hard definition to use. But it's true. I can form it from anything else. The information is still there. I haven't lost any of the information by writing this down or that. I just had to use a lot of storage to hold it. So there's another definition right here, minimal sufficiency. I'm going to write it down right now. But I want you to think about something as I write this down. Why do we care? Why is this important? So, minimal sufficiency statistic is such that this ratio, fx, so this is just x1 to xn, if you will, given our parameter theta, so just general parameter set, whatever you don't know in the distribution, divided by some other realization of data. So a conceptual nether vector of data. This is equal to a constant if and only if Tx is equal to Ty. Now let me put the precursor in here. Tx, T, I'll say, is minimal sufficient if this is true. Tx is minimal sufficient if the ratio of two distributions with different data sets plugged in is constant if and only if this thing is true. So be careful with the ifs in there. So this has to be an if and only if statement right here, but T of x is sufficient if this if and only if statement is true. So a little bit of a brain teaser on what it actually means. But I think it's actually pretty conceptual if we just write down an example. But really, this is the sufficient condition on something being a sufficient statistic. And bend your mind around that. So let me just say that. Again, this is the sufficient statistic, the condition for it. So it's basically saying if I just plug in two data sets, they're constant, then I have equal information in both data sets. That's what it's saying, same statement. Let me remind you, this is a constant with respect to theta. There's no thetas in here. So that looks eerily similar to this other condition that we looked at. Same shapes of those likelihood functions. And so everything's a constant with respect to the parameter that the likelihood is a function of. If and only if this is true, this is the binding condition. This is the necessary condition for it to be sufficient. Let's look at an example. You can kind of see it right here in this thing. I can write this down. Start with this example. We'll plug through a couple of them just to make sure we're on the same page. So f of x in our example is this Bernoulli thing. And so I want to look at this ratio first. So I'm going to look at fx given p over f y given p. I'm just going to write this thing down. This just looks like this. Product p xi 1 minus p 1 minus, apologies, there's no n there, that's a 1. 1 minus xi, I goes from 1 to n, divided by product I goes from 1 to n, p of yi, 1 minus p to the 1 minus yi. We want this to be a constant. So the question is when is this a constant? So when is this true? That's what we're thinking about.
Does n for both y and x have to be the same?
Yes, ma'am. Same sort of realizations that we compare to each other. So absolutely, you'll understand this in just a moment. The question is when is this a constant? What is the necessary condition here? It's not that the xi's are equal to the yi's. So let's look at that. So when xi is equal to yi for all I, this just means for all I, then this thing right here is equal to a constant. So that's cool. All that tells me is that the data itself is sufficient. That's not necessary. If I plug this in right here, so let's write down. I goes from 1 to n, p to the xi's, 1 minus p, 1 minus xi's. If I had done something like this, p to the sum of the xi's, I goes from 1 to 5, 1 minus p to the 5 minus sum of the xi's, I goes from 1 to 5. Not done yet. There's more right here. So a p and a 1 minus p. I'll raise this to the sum of the I goes from 6 to n of the xi's. And then I'll say, n minus 5 things minus sum of the xi's. I goes from 6 to n. Sorry for the messiness on that, but I think you get it. So if I just plugged in that other sufficient statistic right down here, I could have combined all this stuff, and it would be the sum of the xi's would appear in there, n minus sum of the xi's. And so this is a constant as well. So that means that the sum of the xi's, I goes from 1 to 5, and sum of the xi's, I goes from 6 to n, is also sufficient. This thing is a constant. So this is the condition on sufficiency, just rewritten a little bit differently for you. But this isn't what needs to be true for this thing to be a constant. What needs to be true is that sum of the xi's is equal to sum of the yi's. So let me write that down. Needs to be true is sum of the xi's. I goes from 1 to n has to be equal to sum of the yi's. I goes from 1 to n. For star to be a constant. With respect to p in this example. So that's the necessary condition. If the sum of the xi's is the sum of the yi's, that ratio will be a constant. Hopefully you can see that. There's other things that can happen to make it a constant, but that's the necessary condition. I don't need all the xi's to be the yi's. I could exchange them all over the place. I could have a whole different set of realizations of yi's from xi's. I just need the sum to be the same. And they have the same info. There's a mathematical definition. I think it's kind of common sense. So there is a proof in the book. Forget about it. So, unless you want to read through it. But this is kind of obvious. Any questions about minimal sufficiency? Does that kind of clear it up, Elise? Okay. Let's do one more example. Maybe two. Okay. Let's look at the Poisson distribution. I'll write down my sampling model. Q of xi's we'll keep it with theta. Usually we use lambda here, but we're flexi. This is equal to e to the minus theta, theta to the xi, over xi factorial. Xi's in this model are elements of counting numbers. 0, 1, 2, 3, so forth. Theta is positive. It's a Poisson distribution. We use them to count things. So this is the fundamental counting distribution. Most other counting distributions can be derived through mixtures of this. Scale mixtures, additive mixture models. We'll be doing that stuff in class. That's my added bonus to you. You'll learn all about mixtures in this class. Right now, we're just getting the basics, the vocabulary. So Poisson distribution, it's a limit of Bernoulli's when n goes big and p goes small, so it's a rare event counter as well. Interesting stuff. Usually I put an R right there when it's an actual mass function. So let's just look at the ratio of fx to fy. Here's the first step. I goes from 1 to n, e to the minus theta, theta to the xi's, over xi factorial. Over a similar product, but I'm just going to change the arguments to yi's. The question is what is the necessary condition on the xi's and the yi's for this thing to be a constant? So when is this a constant? And I'll remind you with respect to theta. So all you have to do is stare at where the thetas appear. Stuff where the thetas don't entangle the data, that's a constant with respect to theta. So I can instantly ignore that in that. And that makes my heart warm. Because I don't like dealing with factorials. I don't like computing them. I don't like doing mathematical exercises with them buried in. And so they make everything messy and they blow up real fast on your computer. Turn your code into junk. So when is this necessarily a constant is the real question. What do you think, Elise? Can you do it? Just want to analyze this for a second. You're a pro. Total natural. So, and you probably already knew something about Poissons, that we use X bar all the time for doing that, so probably. So yeah, that's right. When is it a constant? The necessary condition is sum of the xi's is equal to sum of the yi's. We could kind of verify that. We could simplify these products and convince ourselves that that's true. So, write this down as star star. Star star is equal to e to the minus n theta. No x's appear there. It's not really all that much info. It does have something to do with the asymptotics of the problem. You would never want to throw that term away, but it doesn't actually tangle up the actual information encoded in the xi's itself. So theta, sum of the xi's. You could write this down if you'd like to. Xi factorial, I goes from 1 to n, e to the minus n theta, e to the sum of the yi's, divided by all these factorials. So you can kind of see it when you write it down that way. And when it's just a constant, well, all I need is those sums to be equal to each other. So it's something we usually do by inspection anyway. So we kind of play around with it and see how much we can reduce it. And then if you wanted to convince somebody, you could come up with a mathematical proof that the time that this is constant is only really depends on the sums of the random variables.
Is it equal to the ratio over omega n in the denominator?
Oh, yeah, thank you. Does that make sense now? Let's do one more example. So kind of like if I say, give me a minimal sufficient statistic on an exam, you're going to kind of build this, you probably just do this. Employ the factorization theorem in your head. See how the statistic depends on the data and hone in on this part real quick. And you go, oh, it's right there. And I can compress this down into the sum. And then when I ask you, prove that that's minimal sufficient, you'll write down this ratio sort of thing and show that it's constant. And you'll declare probably, this is a constant if and only if. Some of the xi's, some of the yi's. Now I understand you might have number theorists in the class that say, that's not good enough. But it's good enough. Anybody a number theorist? Okay. You can take every proof back to the reconstruction of the numbers if you like. So it's good enough for me for you to be able to recognize it and explain it to somebody. Explain it to yourself. Let's do one more example. I think I asked you guys to tell me why you might care about any of this. So here's one thing I used to think. I used to think, and times have changed for me. I do a lot of machine learning, plug-in estimation type stuff, but in my heart I'm a little bit of a Bayesian. And so I have a natural inclination to run off to do Bayes. And I think, oh, my Bayes distribution is always likelihood times prior. And likelihoods have the sufficient statistics shoved in them, guaranteed. I love that. So I get the sufficient statistic for free. Why do I care about mathematical properties of statistics? All I needed to know was about sufficiency. Tell me it's sufficient, it's all the info, I can forget about everything else, right? Why do I care about minimal sufficiency? It's pretty practical. If you believe your model, that's a big caveat here. What we normally need to do is we need to model our data and write down a model first. And modeling is all about diagnostics, looking at residuals and things like that. So once I do all that, then maybe I can declare a sufficient statistic. But it's kind of a fantasy, right? It's like, we don't know that the data came from that. We've just kind of through maybe some engineering decided we've used a whole bunch of IID distributions in mixture formats to represent our data. Dave Finetti says that that's the correct thing. You have permission to do that. It's a proof to say that that is the representation. So I do my thing, I build a model, I look at some residuals, I go, my model's all messed up over in this part of the space, so I need a different layer to my model that gets the data right over in this other part of the space. So I do that, and I go, oh, the residuals look pretty good, pretty happy with all that. So model seems to fit the data. So now I declare this is the sufficient statistic, the minimal sufficient statistic, bless you. Is this just mathematical fantasy? Or is there more to it? Because I thought that it was. Believe this is all just artificial in our minds. That's neat math. I like math too. Like following deductions. I assume something, this is what's true. That's cool. Later on, I learned that it has massive practical implications. That if I ended up coding up, this thing on my computer, if I said, look, my likelihood function is just this. This is my likelihood. I usually write that down like this. I don't care what you call this function, that's what it is to me. So you can write it down with sums, you can write it down differently on the chalkboard, and and it's all exactly the same to me. So in the classroom, I do think this is fantasy. We don't really care, but when I go to encode this thing on a computer, I'm going to be really thankful that I don't product over all the xi's. I'll also be thankful that I don't compute the xi factorials. Right in here. We'll talk about that later. I never even write those things down because it doesn't have any theta in there. The thing that if you are a p-value computationalist, you use those as part of the sampling distribution. Talk about that in the next lecture. But I really like writing this thing down. E to the minus theta, theta to the sum of the xi's. So every time I go in my computer code to evaluate everything, I just evaluate this. I store less in RAM, and I do less computation. So I save on storage and compute by using the minimal efficiency. So I don't know if that's what Fisher was thinking about. I think he was thinking about the math, but maybe he understands all that. And we weren't exactly using the same sort of technology we do today, but this does have massive benefits. But
The e to the minus theta?
yes. Definitely. I'm glad I've got you guys here. So, but I'm going to work with that thing. So I do less compute and I store less. So if you want to waste a lot of time and burn cycles on computers and blow up your RAM, you can tune out. So none of this will matter to you. I do like it when my computer is running for hours and on hours and on hours and on hours, doing something. I love that. It makes me feel like I'm a modern statistician doing all kinds of stuff. But I sure would like to speed it up if I could. So, okay. One more thing. This one's harder. It's in the book. So let's write down this distribution. Let's say given theta is equal to 1 over pi 1 plus xi minus theta squared invert. Xi's can be anything. Thetas can be anything. It's a shift parameter. I move that parameter around, moves this function around.
How does removing the x factorial or doesn't affect the likelihood?
The likelihood is a function of theta. So it's the same shape.
But for given things, right?
Yeah, so that's right. So likelihood is given x. And that's why I like this notation to represent it. So if you were doing something with a mass function and summing tail probabilities, you will need your xi factorials. I just wrote this down as a likelihood. It only depends on theta. Likelihoods are always proportional to something. Likelihoods are self-relative to each other. So you can only discuss likelihood values through ratios. So those xi's would cancel out. So I wouldn't compute that on my computer too, because that's going to be all the time. And it's going to be all the numerical inaccuracy. Just real quickly, how big of a factorial can you compute on a computer and get like an actual number that you could trust?
Depends on your programming language.
Absolutely. So what about your computer and your programming language?
Well, in Python, you can do really large ones.
Like what? They're going to use approximations though, right?
Python uses big integers.
It uses what?
Python uses big integers.
True. So what is the biggest number? You say real big.
I haven't explored these others.
I did when I was in college. So now computers have changed in the last 20 years or so. So the number was 52 for me when I was in college. Now we have 64-bit stuff, a little bit bigger. So it can compute more, but it's not going to be more than like 7. So not too big. So if you were counting just kind of moderate stuff, then computing that factorial is going to be very difficult. A lot of times we do employ approximations. David, you had some insight?
No, we were talking about the number of bits Python uses.
Okay, yeah, exactly. Nerds. So that's good stuff, but it's like More is better, but we're still pretty limited, so computing these numbers can be hard. We'll talk about that a little bit more as we go. Okay, let's go to this example. Anybody know what this distribution is? This is one of my favorites.
Cauchy.
It's Cauchy. It's a type of T. I could have written degrees of freedom up in here and turned it into an arbitrary T and said a T1 is a Cauchy. That's a T1 or a Cauchy. One of my favorite distributions. Got heavy tails. Weird things happen with heavy tails. So if you read books like The Black Swan, Nassim Taleb, that talks about statisticians can't do anything. They don't know what they're talking about. Can't compute all this stuff. Central limit theorem is always wrong for us. He used to work on the stock market in 1988. He lost billions of dollars. So saying that, he's a statistics professor at UMass, and so he's a provocateur as well. So, and in his beginning of the book, he says, we're going to discount everything to do with heavy-tailed distributions. And if you really want to model some uncertainties, build some massive tier tables. So he kind of says we're not going to confront the argument that fixes everything for statisticians. He ends up saying statisticians just use normal distributions effectively. He uses this all the time. So all kinds of my research has Cauchys buried into it. Okay, what do you think the minimal sufficient statistic is for Cauchy? So we just have to write down this ratio, fx, given theta to fy, given theta, and think about what the necessary condition is for it to be a constant. Again, this will be a constant as long as I plug in sufficient statistics into everything, but I want to know what the necessary condition is. And so this is just 1 over pi. You'll start to forgive me when I start messing up the normalizing constants and writing them down, because they always cancel out all the equations. So we'll try to get this one right. Xi minus theta squared inverse. We're going to product this up. I goes from 1 to n. And we'll write down a similar product in the denominator with y's.
Cool data set.
So when is that a constant? Harder to do. Anybody want to take a guess? What the necessary condition is? Probably trying to Taylor expand this thing right now, right? Maybe. It's kind of hard to, I don't know if that's what you're trying to do, but I know that's what I would run off and start doing, is trying to Taylor expand it and figure out, is there a neat cancellation that happens? Are there neat combinations that happen? And it turns out there isn't. There's nothing you can do. So this is a constant with respect to theta, if and only if the xi's are equal to the yi's.
So could do we just take the order statistics to be the same?
You could say that too. So that's a good way to say it, is that the order statistic is sufficient, but I can take the original data. So I don't actually need the ordering to be the same of everything. I just need the order statistics to be the same. So really, Ben's right. Xi is equal to yi. So these are the order statistics. So the order doesn't actually matter. I don't need xi and yi to be exactly right. So you scooped me. So these are the order stats. Why? Because this product is the same in any way that I write it all, any way that I multiply it. Same thing. This is going to be for all I. That's my notation for that. Make sense? Now, if you're a number theorist and you really like functional analysis, you're going to try to prove that to yourself. And convince yourself that you can never, through a polynomial expansion or anything like that, make this any simpler. So if you're dealing with a Cauchy distribution in computer code, this is a little bit worrisome. I said I do it all the time and I'm interested in computation. And so I don't like computing this big product. And I don't actually do it in my computer code. So I have an auxiliary method that does all of this. It's equivalent. And maybe we can talk about that later. We'll certainly do it in my 5444 base class. So there is a way to handle Cauchy distributions efficiently in code without having to write down the product every time and blowing up your code. Okay, but you can't simplify it any further than this. It's still going to be the ratio of these products. That's it's a constant. You can't compress the data anymore. Why? If you've ever sampled from Cauchys, you'll understand it. So what happens with a Cauchy? Well, when you draw the histograms of everything, Cauchys kind of look like this compared to normal. Bless you. They actually look a little tighter than that and more close to normals than I've drawn it right there. But you'll start to collect data from your Cauchy distribution and building your histogram up, and you'll go, ooh, that sure does look normally distributed. And then all of a sudden, you get a value over here, way out there. You sample a whole bunch of times, it's this nice little shape, and then all of a sudden you get a value way across campus. So Cauchys really do throw out these anomalous points. And so in seeing those points is the most important thing. So when I see outliers, so-called outliers, but I think it's really part of the process, I do not trim those off and model it by normal stuff. That's what Taleb says we do. That's what he did. So he's guilty. So, and then blames everybody else. So anyway, Cauchys are fascinating distributions. So you can't reduce the dimensionality of the statistic. In the book, I assign a problem that says, for a general location scale family, what is the sufficient statistic, the minimal sufficient statistic? And this is a location scale family. We just learned that the order statistic is the minimal sufficient statistic. Normals are also location scale families. A whole bunch of these out there. And there, x bar and s squared are the minimal sufficient statistics if you didn't know both parameters. That's outlined in your book, so please go through that. So it's a general statement. So usually when we ask questions as mathematicians, we're asking about the most general cases. So this is your counterexample to the compression quotient. Okay, let me tell you about something less meaningful, ancillary statistics, unless there's any questions. Ancillary statistics. And I want to give you an example. But basically what these are, if I'll say Sx, so some function of the data, some statistic, is ancillary, then the distribution so I've got all my data, my xi's, coming from some model. It has theta in there. I see a whole bunch of them. And I compute this statistic. I can figure out what that distribution is. It's a transformation. And if that distribution doesn't have any dependency on theta, it doesn't appear in the distribution, then it's ancillary. So does not depend on theta. This is a transform. Usually when you transform things that originally depended on theta, it would be natural to think that your transformed thing has some dependence on theta. Sometimes it does not. And this theta will disappear. When that's true, we say that this statistic right here is ancillary. Let me show you an example. This example stems from the example in chapter 5. I hope you agree. It's slightly different, but the mathematics is identical. So let me say a few things about the example. We looked at this example very early in class. This is that triangular thing that shows up in chapter 5 with the range and the mid-range. So consider xi's come from a uniform distribution, and I'll vary in my theta right there, theta plus 1. So this is going to be xi's that are distributed uniformly between theta and theta plus 1. Because this interval length is 1, I know what the height is. It's 1 as well. So fxi, given theta, is equal to 1. Okay, so that's my sampling density. Pretty simple problem. The mathematics in the problem in the book, make that a 0 and make this a theta. All the integrations, everything that I'm going to say today falls right out of that, and just plug into the formulas that you get. So I want to see if you can do this. I'm not going to go through the integrations here, but I want to ask a few questions about this. Example. So what's minimal sufficient? Just to make this a little bit easier, so you can see there's parts of this equation you might forget about. Xi are going to be between theta and theta minus 1. I want to give you a quick warning on this. It doesn't matter if I include the endpoints or not, same measure. Probability of getting those is 0. I never really stress. But when you see the parameters show up in the bounds of an equation, do not forget about that. It changes everything in the problem. A lot of times we're just dealing with whatever this thing is. I should just stare at that real quickly. And notice there's no real information about theta right there. Where's the information about theta? The bounds. So when I say, please write down the likelihood for this function, and people do this. Likelihood of theta given x, and I'll say it's proportional to I goes from 1 to n, fxi given theta. It's true. Open up my sleeve, which is 1 to the n, which is 1. And if my time as being a statistician is correct, somebody will do this on a midterm or a final, and it will freak me out. I know, it's ridiculous, right? Zhang is like, who would possibly do that? I see it all the time. So number one mistake in this class is writing down likelihoods that don't have the parameter in them. So what's the correct likelihood? Somehow need to account for this. What's that? Yeah, I like that. So what I would normally do right here is I go from 1 to n, and then I would have all these indicator functions. Xi greater than theta, less than theta. There's definitely information in there. There's a dependence of theta on the xi's. So staring at that equation a little bit, this might help you to understand what is the sufficient statistic. So I always write down this same formula. On the chalkboard, it always looks the same to me. It's a function of x, or it's a function of theta, and depending on which one I'm envisioning it as, it's either a likelihood or a sampling distribution. Saying that, when I'm answering this question, I'm looking at the interplay between x's and thetas, how they both show up in this equation. So I just write down this equation, and I stare at it, and I try to figure out what the minimal compression of information in this thing is. What do you think the answer is? Maybe the maximum. So I've got a whole bunch of data in here. And so maybe it's that.
both the min and max?
Maybe it's the min. This also tells me something about theta. So in the book problem that's between 0 and theta, only the maximum is informative. And since this problem has the parameter on both sides, it's one of those two things. And so it's whichever one is closest to the boundary. And so you might say this, xn or x1, depending on who's closest. What dimension is this? It's 1. It's whichever one is closest. I can't answer the question until you show me some data. And so, don't really know. They're both informative. So I kind of need to hold on to both of them. But it really is whichever one is closest is going to be the binding condition. But you need to hold on to the min and the max, and you needed all of the data to get them. So kind of interesting problem. So we can just write that down a little bit differently. And I can say this product, f of x I given theta, I'll say these indicators right here, xi between theta and theta plus 1, I can write this a little bit differently. I can write it like this. That xn, the maximum, is less than theta, and x1, this is theta plus 1. And the minimum is greater than theta. We'll put the equal signs on there. Same indicator function, same functional evaluation. I can multiply two products together if I wanted to break that into two functions. But that's what it really is. And so, you see that information right there. We can never get rid of it. I don't really care after you've ordered everything. The only information about theta is on the boundaries. So that's my likelihood function. So let me ask you this. If I compute these two statistics, the range, xn minus x1, and the mid-range, which is just the average of the two extrema, can I get back xn and x1? Of course you can. So if I give you these two things, you could easily compute xn and x1 for me. It's just algebra, linear solve, no big deal. Back of the envelope calculation for you guys. So all the information is in here too. So these are minimal sufficient as well. We have all that information.
But that would be like two-dimensional, wouldn't it?
Yeah, but it's the same thing that we just said over here. Those guys. Two-dimensional, kind of. Whichever one is closer is the binding condition. But without seeing any data or anything like that, not knowing what the distribution is, I don't know. So I need to hold on to both. So if I'm going to hold on to both of those things, I can compute those from this without any extra information in it. Let me ask you a question, just conceptually. Does this have any information about theta? Feels like it doesn't, but obviously in the presence of the mid-range it does, because I need both of those things to get back to x1 and xn, order statistics. on its own, if you just think about this problem, I want to know what theta is. The range is telling me about the variability of the distribution. So I can slide this thing around, changing what theta is. It's a shift parameter. Keep the width the same. And this is going to have the same distribution. So it doesn't depend on theta all by itself. So the range on its own is ancillary. But the range does have information provided the mid-range. I want to go through an actual calculation for you guys so you can appreciate that a little bit more. So this definition is distribution of an ancillary statistic doesn't depend on theta, but just be a little bit more careful about that because it could provide the information in lieu of something else. Could be part of a sufficient statistic. Bassu's theorem in the book, I want you to read through it. I don't want to dwell on it. I won't ask you for a proof to this, but it basically is this statement of when a sufficient statistic is complete, then it's going to be orthogonal to every ancillary statistic. And that ancillary statistic can never help you no matter what you do with it. Saying all of that, what do I really care about when I do statistics? I care about min sufficiency. Nobody's ever come to me and said, well, you did all this computing and you've used all the information. I was wondering if your statistic is complete. It's never happened. I don't think it ever will. Nobody cares. So, but it's interesting mathematically. Let's pick up there next time. We'll carve out an example. I'll go through what I just said in great detail through a simplified example. And then I think we might transfer over and talk about the likelihood principle. Thanks, you guys.
Are you doing a review section tomorrow?
Yes, I will. So review tomorrow if you guys are up for it.